Picture a world of giant reptiles, flying pterosaurs with 40-foot wingspans, while beneath the waves, fierce predators called mosasaurs prowled the seas, and dinosaurs roamed the land. For more than 100 million years, creatures like these ruled the planet. And then, they were gone, lost in the shadows of time. Their extinction, a mystery for the ages. This is Gubbio, a sleepy Italian town. Not a single giant reptile in sight. Still, the past is everywhere you look, in the medieval palaces and churches, the homes and narrow streets, while an even deeper past lies nearby. Just outside of Gubbio, Alessandro Montanari is looking for that distant past. He's a time traveler, moving towards the lost world of the dinosaurs, its ancient history written in these limestone cliffs. Gubbio's deep-sea limestone, now exposed by the side of the road, became a magnet for scientists. Especially this site, that may seem ordinary, but holds one of the strangest features to confront the geologist. A thin layer of dark clay. In the 1970s, the clay captured the attention of an American geologist, Walter Alvarez. He was trying to determine the relative ages of the limestone layers by analyzing the fossils left by tiny shelled sea creatures. Called foraminifera, or forams for short, they're among the most common ocean plankton. When they die, their shells become part of the sediment. Since many different species have evolved over the ages, they can serve as markers of geologic time. But as Alvarez studied them, he noticed something striking. The same questions were being asked 1,500 kilometers away, in Spain. On the Atlantic coast, outside the town of Zumaya, Dutch geologist Jan Smit was studying the forams from a different ancient sea. Their fossilized shells formed these limestone rocks, which, like Gubbio's mountains, were once at the bottom of the ocean. Now exposed, they represent over 1 million years of a geological time period known as the Cretaceous. Like Alvarez in Italy, Smit had also found a strange clay layer formed at the same time, which told a dramatic story. The KT boundary found at the bottom of this gray layer marks not only the end of a period, the Cretaceous, but also of the Mesozoic era, a much longer stretch of time. The history of animal life on Earth has been divided into 3 such eras: early life, or Paleozoic, the age of dinosaurs, or Mesozoic, and the era of mammals, or Cenozoic. The Cretaceous-Tertiary boundary lies right in between these 2 eras, marked here by this layer of clay. In Amsterdam, the change at the boundary becomes clearer when Smit takes a closer look at the evidence. In his lab, he analyzes forams extracted from the limestone. Under the microscope, the rich diversity of fossilized shells from the Cretaceous snaps into focus. Some 4 dozen species appear below the boundary, but above it, there's a different world. These are the foraminifera from just below the boundary, and these are from just above the boundary. Only a few species have survived into the Tertiary, and they're much smaller. A layer varying in color and thickness, and found around the world. Walter Alvarez also believed it was a silent witness to the end of an era. The key question was, how long did it take to form, for the world to change? To find out, he sought help at the University of California at Berkeley from a Nobel Prize-winning physicist, someone he knew pretty well, his father, Luis Alvarez. Luis loved a good mystery, no matter what field it was in, and that's how physics joined geology in the quest to explain the KT extinction. The element was iridium, which falls steadily in an invisible rain of cosmic space dust. If the layer had taken thousands of years to form, Alvarez thought there might be just enough iridium to measure. But when the clay was tested, the scientists were stunned to find it contained 30 times more iridium than the surrounding rock. Moreover, samples from other KT sites had similar levels, too much to come from ordinary space dust. What could explain so much iridium deposited around the world? Perhaps a catastrophic event in outer space. Alvarez wondered if a supernova exploding nearby might be responsible. A supernova would have also deposited a rare isotope, plutonium-244. But testing revealed there wasn't any. There are hundreds of asteroids whose paths cross the Earth's orbit. Their sizes range from a few meters to hundreds of kilometers across. The answer was sobering. An asteroid 10 kilometers in diameter, as large as Mount Everest, and weighing hundreds of billions of tons. Still, how could something that size wreak havoc on a large planet? Because traveling through the vacuum of space, it would have slammed into the Earth's atmosphere at 80,000 kilometers per hour, 20 times faster than a bullet, heating the air to several times the temperature of the Sun. At impact, the energy released would be equal to about 100 million nuclear bombs exploding at once. A huge mass of pulverized debris would have been blasted into space, some of it orbiting the Earth before raining back down. The debris may have blocked out the sun for months. Photosynthesis would have stopped. Plants, plant-eaters, and then meat-eaters would have died. This was the asteroid impact hypothesis for how the Mesozoic era ended. A big idea that was just too big for some. The controversy would continue for years. To convince the skeptics, more evidence was needed. One criticism of the KT hypothesis was the lack of a crater the right age, type, and size. Alvarez thought it should be 200 kilometers across, bigger than the state of Connecticut. How could you miss that? The search for fresh clues led here, to Texas, along the Brazos River, some 300 kilometers from the Gulf of Mexico. 65 million years ago, this was the bottom of the sea instead of grazing land. In the early 1980s, scientists noted unusual deposits of sediments across the river basin. Intrigued, Alan Hildebrand, then a graduate student in geology, came to investigate. It's actually easy with trash tracks. Along the banks of the river and its tributaries, he examined exposures of the KT boundary different from those seen elsewhere, and saw something on top of the Cretaceous mud and rock that had once accumulated on the sea floor. An untrained eye might see this sediment, and never look twice at the protruding boulders. But Hildebrand saw evidence of a catastrophic event. If an asteroid 10 kilometers across landed in the sea or at the edge of a continent, it would displace incredible amounts of rock and water, causing tsunamis over 100 meters high. These giant waves would have crossed the sea with the speed of a jet, ripping up the sea floor, moving tons of sediment. As that debris came to rest in what today is the Brazos River basin, it would have mixed with ejecta falling from the sky. Hildebrand was hot on the trail of every new piece of evidence. Next stop, Haiti, where he investigated a report of volcanic rocks. As he suspected, they were actually ejecta, full of shocked minerals and spherules. They also contained melted rock called tektites, another telltale sign. more evidence that a strike had occurred somewhere around the Gulf of Mexico. But somewhere wasn't precise enough. Ironically, a key clue discovered by another geologist had long been overlooked. Years before, Glenn Penfield had hunted for oil on the Yucatan Peninsula in Mexico. From the air, Penfield saw nothing unusual. But his instruments measured differences in gravitational fields and revealed the features of a giant buried crater. It was Hildebrand who eventually followed up on Penfield's work. Rock samples from the area Penfield identified showed all the signs of a high-energy impact. After years of speculation, the crater had finally been found. It was named the Chicxulub crater after a village built over its center. The asteroid crater had finally been found, but important questions remained. Which species were wiped out at the end of the Mesozoic? Which survived, and why? The search for those answers led to the Badlands of the Dakotas and Montana in the Hell Creek Formation. Its eroding buttes hold fossils of plants and animals that lived during the last million years of the Cretaceous and beyond. When paleontologist Kirk Johnson discovered this KT boundary with its telltale spherules, he found the dividing line between two vastly different worlds. This arid landscape was once a wet, lush forest. Crack open some rocks, and you'll find the leaves of plants and trees that flourished here over 65 million years ago. Look at that. You can even tell what insects ate them. Holy cow. The challenge? Connecting their fate to the KT boundary. The clues? Their fossilized remains. Scientists know that 22 types of dinosaurs lived in Hell Creek, including Triceratops, Tyrannosaurs, and this duckbill, some 9 meters, or 30 feet long. The more complete the skeleton, the easier it is to reconstruct the past. But discoveries like these are extremely rare. For dinosaurs further away, death may have been delayed, but not for long. Soon, vaporized ejecta and smoke from fires filled the air. Without light, anything dependent on photosynthesis, on land or in the sea, was vulnerable. As food chains collapsed, giant reptiles still alive died off. The Mesozoic era, the age of dinosaurs, was over. And there were other radical changes. In Kirk Johnson's Denver lab, you can see what happened to plant life. Samples taken from below the KT boundary show a high diversity of pollen grains, stained here in red. But above the boundary, this earlier diversity disappears, reflecting the extinction of 60% of all plant species. Where flowering plants once thrived, ferns took over first. Fern spore, fern spore, fern spore. Unlike pollen, fern spores can germinate on a barren landscape, devoid of living plants. In this new post-impact world, the niche that dinosaurs left was waiting to be filled. In that million years of recovery, the small inherited the earth. It was the beginning of the age of mammals. Eventually, larger mammals dominated the land, just as dinosaurs had done before. And among them were primitive primates, whose evolution would lead in a very promising direction, at least for humans.